tilde definition. I missed while you were talking.
So x is distributed the same way that the normal x is distributed. Y is distributed the same way that the normal y is distributed. But while x and y are joint random variables, these are independent random variables. So I'm constructing a fake distribution that has the same marginal densities, marginal distributions of x and y individually, but where these are independent. So it's sort of like when x and y are independent, we sort of have this relationship. If you think about generating such random variables, we would first generate x, and then we would generate y given whatever x we have. Over here, what we can think of is x tilde is generated the same way that x is, and y tilde, and now there's no relationship here. What I would do instead is I would generate some x tilde prime and generate y tilde based on that, where x tilde prime has nothing to do with x. So that would be one way to generate such random variables. So in other words, y now would have, if x tilde has the same distribution as this x, then y tilde would have the same distribution as y, even though x and y would be independent. All right. The probability that such independently generated random variables is less than this, and for n sufficiently large, the probability that such independent random variables is in the typical set would be greater than or equal to 1 minus epsilon 2 to the minus n times mutual information plus 3 epsilon. Okay, so basically, up here, the normal random variables, the probability that they're in the typical set is roughly 1. Down here, the probability that these independently selected random variables, the probability that they are also in the typical set, if I just select them independently, is somewhere around 2 to the minus n times the mutual information. So this is the mathematical importance of mutual information. Basically what this is going to say is that if I, down the road, all of my codes will be based on random coding arguments. In other words, I'm going to randomly select x to convey my messages, and then, I'm going to randomly select these x's to convey my messages, and the y's will be based on those. All of the x's are going to be independent. So therefore, if there's a message that if there's a code word that I could send but doesn't correspond to my existing message, the probability that that code word, which is selected randomly, is jointly typical with what I received, even though that's not what I sent, so therefore these guys are independent. The probability of that happening is roughly 2 to the minus n times the mutual information. So that'll put an upper limit on how many code words I can have in my code book. But we'll see exactly how that works later. For now, it's important to just notice that here's the first time that mutual information actually comes up. Now, I promised you that I would define the typical set. So remember, that's just the statement of the theorem. We still have to prove this. But I forgot to mention the definition of the jointly typical set. epsilon to the n is called the jointly typical set, and it consists of the set of all pairs of sequences, x1 to n, y1 to n, in the channel input alphabet, Cartesian product with the channel output alphabet, such that, okay, firstly, intuitively the explanation of this set is the following. The sequence x is itself typical, the sequence y is by itself typical, and the two sequences together are by themselves typical, or are together typical. So it's not merely the generalization of the typical set where it's not merely the generalization of the marginal typical set for one source where it's like all of the individual sequences must be typical. Here we have this one must be typical, that one must be typical, and they both together must be typical. So mathematically what I mean by that is this, such that magnitude minus 1 over n log p x1 to n minus h of x is less than epsilon. So remember, this is the criterion that says that x is itself typical. Basically what this means is that the probability of x is close to average. Minus 1 over n log probability of y from 1 to n minus h of y is less than epsilon. So y is itself typical. In other words, y by itself has probability close to average. And negative 1 over n log the joint probability between x and y minus the joint entropy between x and y is less than epsilon. So that there is the jointly typical set. It's only complicated if you think about it. What are we really excluding here? We're excluding cases where somehow x is atypical but y is typical, or x is typical and y is atypical. So those are the cases that we're excluding. Presumably they would have very little probability anyway, so it doesn't really matter. But we're just ensuring that x is by itself typical, y is by itself typical, and together they are typical. Yes?
Is it 1 over n for the last one as well?
Yes. So it's, we're counting pairwise here. So remember, h of x and y is the expected value of this, log t x1 to n, y1 to n. This separates into n terms, so the average over that is 1 over n. Okay, so let's prove our theorem. So, proof of the first statement, let's remind ourselves what the first statement was. The first statement was the probability of any particular sequence being in the typical set has to go to 1 as n goes to infinity. And we proved that